What?
Hi, Mr. Jordan.
Okay, so let's listen up here, folks. First of all, there is no eating or drinking in the lab, which we all know. Okay. Right. What I want to do today is go over the short presentation on osmosis and diffusion. We should all know what that is, right? Remember that from last year? And then I have setups at the lab tables for you. You're going to have to do 2 people to a setup, which means we're going to be having our face shields on, and you're going to need to wear gloves because we need to share the scales. Okay? All right, so I'm going to share the screen with you so we can go over that presentation. So let's do that. Okay, so osmosis and diffusion. In keeping with our discussions concerning water, we know that diffusion is the movement of particles, right? Particles are always moving, kinetic energy. And they're going to move from an area of high concentration to low concentration, down their concentration gradient, until equilibrium is reached. Okay? This happens passively, so it's passive transport, no energy required by the cell. Right? No energy required to make diffusion happen. And again, I put this in the classroom, so you should be able to access this as well. Osmosis is a special kind of diffusion. It's the movement of water from an area of high water concentration to low water concentration through a semi-permeable membrane. Again, passive, no energy required. Okay? Oh, there's a breeze. Okay, so if I have this set up here with these U-tube contraptions, and there's a semi-permeable membrane between the right and left arms of this thing. If I have low solute or low sugar concentration on this side, higher on this side, the question is, which way will water move? Remember from last year, we said water always moves towards the hypertonic solution. Water always moves towards the hypertonic solution, the more concentrated solution, because it's trying to dilute it down, right? So water is going to move in this direction. And you can see that over here, right? And that is why. If the sugar doesn't get through the membrane, the only way to reach equilibrium between the 2 arms here is to move the water. Okay? Questions? Just remember, always moves towards the hypertonic solution. Okay, that's important when we do our little dialysis tubing bag things, right? Okay. Again, this is the same thing here, right? We have a selectively permeable membrane. We have lots of sugar here, less sugar here. Water is going to move this way to the hypertonic solution. Okay. Molarity. When we're talking about concentration, we use this term a lot, molarity. Molarity means moles per liter. And a mole of a substance is equal to the molecular weight of that substance. Okay? So for example, sodium chloride has a molecular weight of 58.5. That's 1 mole. We know how to figure out what the molecular weight of something is. You have to look it up on the periodic table and add them together, right? Okay. Glucose, for example, has a molecular weight of 180 grams. That's 1 mole of glucose. So if I want to make a 1 molar solution of glucose, how would I do that? $180 grams into 1 liter, right? That would be a 1 molar, right? Molarity is always per liter. So 1 molar would be 180 grams in 1 liter, okay? Ionic versus covalent substances. An ionic substance will completely dissociate in solution. Why is that? Like sodium chloride, it's going to come apart. Are you going to get sodium and chloride ions? Why does that happen? Because water's polar, right? So if it's an ionic compound or an ionic compound, it's gonna completely dissociate in water, right? Salt completely dissolves in water, right? However, if we put glucose in water, it also appears to dissolve, doesn't it? Right? It doesn't dissociate. It gets surrounded by water because glucose isn't an ionic compound. Okay? It's not like we're going to have little carbons coming off or little hydrogens coming off. It gets surrounded by the water molecules. Okay? Again, 1 molar solution of salt would be 58.5 grams in the liter. It would be 180 grams in a liter for glucose. When we talk about whether or not something dissociates or it dissolves in water, we can talk about its osmolarity. Okay, that's what that's called. And when we're talking about osmolarity, we talk about hypertonic, isotonic, hypotonic. Do you remember these? Right? Hyper, high number of solute molecules. Hypo, low number. Iso, the same. Right? I know we talked a lot about this last year, but just a refresher here. Okay? You need to know what those terms mean. Questions? Okay. And again, just remember that water is always going to move towards the higher concentration, towards the hypertonic solution. All right? Again, I put this in the classroom so you can view this thing, just to refresh your memories. Again, this is a picture from the text. If I take this happens to be a red blood cell, is the animal cell, right? And I put that into a hypotonic solution, meaning the blood cell is more concentrated than the environment. Water is going to move into the blood cell, right? And it's going to explode. That's why, remember, that's why you don't get, if you're dehydrated, they're not going to give you an IV of pure water, right? It's going to blow up all your red blood cells. If I take that red blood cell and I put it in an isotonic solution, meaning the concentration inside the blood cell is the same as the concentration outside the blood cell, then you're going to get water moving in and out at the same rate. That's isotonic, right? That's equilibrium. So if you're dehydrated and you go to the hospital, they're going to give you an IV of 0.7% sodium chloride, which is isotonic to your blood. Okay? And then finally, if I put that red blood cell into seawater we know is very hypertonic, right? There's a lot of salt in seawater. So what that's going to do is it's going to draw all the water out of the red blood cell. It's going to move to the hypertonic solution, and red blood cells shrivel up. Okay, remember that? Okay. If we're talking about a plant cell, if I put a plant cell into a hypotonic solution, water's still going to flood in, right? Because it can get in through the cell membrane and the cell wall. But the cell's not going to explode because it has that stiff cell wall to protect it, right? So what happens is it becomes turgid, which is sort of the normal condition for a plant cell, right? That central vacuole is full of water, the cell's nice, the plant looks healthy, right? If I take that plant cell and I put it into an isotonic solution, water in and out at the same rate, we call that flaccid. So the cell wall isn't being pushed out, it's just kind of there, right? The cell's not going to shrivel up, it's not going to be expanding. And then finally, if I put that poor plant cell into some seawater, all the water from that central vacuole and all the water from the cytoplasm goes out. The cell doesn't shrivel up though because of that cell wall, right? But the cell membrane pulls away from the cell wall and shrivels up. And we call that plasmolysis. Remember that word? Okay? Again, this is just kind of review here. We can also talk about the diffusion of gases. And that depends on a couple of different things. The concentration gradient, the increase or decrease in concentration from one point to another. The amount of surface area available for diffusion. And the distance that they have to travel, which depends on the molecular weight of gas. Diffusion through the air happens very quickly, as opposed to diffusion through the water, right? So if I were to open something really smelly up here, like clove oil, remember clove oil? Yay, remember that, right? No? Did we use clove oil last year? Yeah, we did. If I open a big bottle of clove oil and I set it up here, in a very short period of time, in a matter of a couple of minutes, the whole room is going to stink like clove oil, right? Happens very quickly. It's light. Those particles get into the air, and they're going to fill the space. Okay? And we don't ever want to spill clove oil in the lab. This is just something from the lab manual. HCl has a molecular weight of 36.5. Nitric acid, NH3, has a molecular weight of 17. Because that's so much lighter than HCl, it's going to diffuse much faster than HCl. Okay? This we're not going to do because this is actually, it can explode. So we're not going to do this particular part. Yeah, there's a little lab exercise where you put you saturate cotton balls and put them in the ends of two different, of a tube. And then you wait for the gases to meet in the middle. And then they make like a precipitate. Yeah, but it could also explode, so we're not going to do that. Yeah, that would be cool. Temperature can also affect the rate of diffusion. And why is that? What does temperature do to like the water molecules in a solution? So you got to yeah, right? So if you heat something up, you're going to increase the kinetic energy, right? So they're going to be moving faster. So diffusion happens faster the hotter you get. So I can put this little block here of whatever this stuff is, some kind of jello stuff here, but this is cold. This is more room temperature. If I heat it up, it diffuses much more quickly because those molecules are moving around more quickly. Okay? And here's what we're going to be doing in the lab. So we're going to look at osmosis by using the dialysis membrane tubes. And you remember those are just strips. Remember the most tedious part of that was getting them open? Yeah, you gotta do that again. So the dialysis tubing has pores in it that are big enough to allow some things to come through. Others might be too big to fit through. So you are going to fill your dialysis bags with varying concentrations of sucrose, and you're going to put them into water, and you're going to see what happens. You're going to mask them before you put them in. You're going to mask them when you take them out. We did this last year, right? Okay. And we're going to look for changes in mass. Okay. And it should be noted that sucrose is too big to move. So the only thing that's going to be moving in your experiment is water. That's what we just said. I'm not going to go through predicted results right now. And we'll do facilitated diffusion later because I don't want to get confused with that. Okay? For my remote learners, if you can hear me, I have put a virtual exercise in the classroom for you guys to work on. So when you have the opportunity to do that, please start working on that. Do you guys have any questions?
No. Do we work on the assignment right now?
Yeah, you can.
Okay.
You can. Or, I mean, what time is it for you, Leo? It's 9 o'clock at night there, isn't it?
Yes.
Yeah, it is.
You don't have to work on that right now, Leo, when you get a chance.
Okay. So
Okay.
what's our homework again?
Say that again.
What's our homework?
The homework questions are in the classroom.
Okay. So it's chapter 2 and 3.
Yes.
Okay.
Okay.
Okay. I didn't see the assignment. I just saw an outline, and it says it has a test on the September 17th for the chapter 2 and 3.
Open up those PowerPoints. The questions are at the end of the PowerPoint, just like last year.
Oh, okay. So it's on the Plus portals.
Okay, you should see the PowerPoints. If you open chapter 2 up, there'll be questions at the end of that. Chapter 3, there's questions at the end of that.
Oh, okay. I see it.
Okay.
Yeah, I got it. Yeah.
So I'm going to sign off now, Leo and Chris. If you have any questions, just email me, okay?
Okay.
All right.
All right. Have a good day, people.
See you.
Do.
Okay. Thank you.